Today, I would like to tell a story about an inverse spectral problem where I will talk about more specifically the stability. And this is a joint work with Hadrian Quan from UC Santa Cruz, Teemu Saksala, who was my postdoc mentor now at NC State University, and my academic sister, Lili Yan, who's also now at NC State. Okay. Yeah, so my talk will be divided into four parts. First, I will give a very brief introduction on the stability in inverse problems, what that generally means, and then I'll move to talk about the main results. And after that, I will discuss a little bit about the proof, which contains the last two parts. Okay, so what do we mean by stability in Hölder problem? So let's sort of now consider this conductivity equation in a Euclidean setting of dimension 3 or higher. Let's now assume that also this omega is a bounded open set with smooth boundary. So what we can measure for the conductivity equation is this Dirichlet-to-Neumann map, which maps the Dirichlet value F to the Neumann data, which is the product of our unknown conductivity and the normal derivative of our solution. We take the product and measure it on the boundary. Okay, and for uniqueness question in inverse problems, as we probably know, is if for two sets of coefficients, gamma 1 and gamma 2, they have the exact same Dirichlet-to-Neumann map, the uniqueness question would be, can we recover gamma uniquely in the whole domain? But in reality, we cannot expect the measurements to be 100% accurate. This is probably due to some nature of measuring devices. We can't expect totally accurate. So the more interesting question, or the more practical question, would be, if we know two measurements are close in a suitable sense, that's why I put the quotation mark here, then what can we say about gamma 1 and gamma 2? In other words, how close can they be if the corresponding measurements are close? Okay. And that question was addressed in 1998 by Alessandrini. Here, in his result, he assumed that suppose there are two conductivities which are sufficiently smooth, and those are bounded, those satisfy some a priori bounds, then what he was able to show is the L infinity norm of the difference of these two conductivities is bounded above by a log function of the norm of the difference of the two measurements, provided that the difference in the measurements are sufficiently small. Okay, and because of this log function, many people call this log stability. I don't work in numerics, so I'm not so mad at it, but there are many people working in numerics who are not quite satisfied, because log stability will create some issues when it comes to like reconstructing the conductivity in the high resolution. Okay, so a question will be, now that log stability is fine but not great, can we do better? It was proved in 2001 by Mendak. But by Mendak, he said that the answer is no. If we consider the DM map for the conductivity equation, then this log stability is as good as we can do. But if we consider another type of data, in this talk more specifically the spectral data, then we could get a better stability, more specifically Hölder, if we consider the spectral data for an elliptic operator. More specifically, I'll consider the magnetic Schrödinger operator in this talk. Okay, yeah. And so now let me start discussing our main result, and throughout first let me fix some notations. Throughout the talk, I'm going to assume a manifold M with a Riemannian manifold M to be a known simple manifold of dimension 2 or higher, which has smooth boundary. In other words, in this talk, we're not going to address the more difficult question, which is, does the spectral data determine the metric? We're not going to answer that. Okay, and also throughout the talk, I'm going to use this capital letter A to denote a one form with real value coefficients, and Q to be a real value L infinity function. Okay, and now let's denote D to be the exterior derivative and define the map. Say dA to be the sum of D and I. Here, this I means the imaginary unit. Okay, what is the PDE we're going to consider in this talk? That's what we call the magnetic Schrödinger, which is a composition of dA star dA plus Q. And when we write out the dA star dA, we'll get an elliptic operator, more specifically this minus Laplace Beltrami operator. Okay. And this operator is also self-adjoint. And we're going to exploit this fact quite a bit in this talk. Okay. And in the previous slide, I mentioned the word simple manifold, and this is a very specific geometric setting. So let me discuss what that is. By definition, what a simple manifold is a smooth connected compact manifold with smooth boundary, and the boundary not only is smooth, but is also strictly convex. And each pair of points is connected by a smoothly varying unique distance minimizing geodesic. There are quite a few examples of simple manifolds. For example, if we take a polar cap of the Earth, that's a simple manifold. But the entire Earth is not a simple manifold, because the North and South Pole, they're what we call conjugate points. And one necessary property of simple manifold is that there will be no trapped geodesics and there are no conjugate points. Okay, and also we can also think simple manifolds as the Euclidean disk, because any simple manifold is diffeomorphic to the disk. Okay. Now let me move to discuss what is the type of data we're using for today's talk. Okay. So this magnetic Schrödinger operator is self-adjoint and has compact resolvent. So its eigenvalues are all real. And also let's denote of phi to be the normalized eigenfunction of the magnetic Schrödinger operator corresponding to the kth eigenvalue, so that the set of all eigenfunctions form an orthonormal basis of the space L2M. Okay, and let's also denote psi to be the Neumann trace of the eigenfunction. So we're taking the Neumann data, measuring the boundary. And the boundary spectral data consists of two elements. One is we're taking all the eigenvalues from the magnetic Schrödinger operator, and we're also taking the Neumann trace of each eigenfunction. Okay. And the question is, can we prove stability for the potentials A and Q in our simple manifold M from this boundary spectral data? The answer is not quite. We can prove A stability, but not for A and Q. So there is indeed an obstruction to uniqueness when it comes to the stability of the magnetic potential A. This might be also a well-known fact, but so let me recall what this obstruction exactly is. So let's take now a C1 function, say V, which vanishes on the boundary of the manifold. Then from straightforward computations, we can show that if we conjugate our magnetic Schrödinger operator by e to the IV, then what we get is another magnetic Schrödinger operator. Now our one form has a shift by dV. Here D is the exterior derivative. And also, not only do we have this new magnetic Schrödinger operator, but also the spectral data for the new magnetic Schrödinger operator will be exactly the same as the spectral data of our original operator. Okay, so these two facts means that we cannot recover A uniquely. Q is always okay. Okay, so what can we recover? There's a well-known decomposition of one form of vector fields by Sharafutina. So what he proved in 1994 says if we have a complex valued vector field, then we can decompose this vector field or one form uniquely into the sum of two parts. One is what we call the solenoidal part. This part is divergence free, and another part is what we call potential part. That's the exterior derivative of a function phi, which vanishes on the boundary of the manifold. So, facing this obstruction unique to uniqueness, the best result we can hope to get is a stability for the solenoidal part of A and the potential Q in a suitable norm, which I will mention in a few moments. Okay, and in stability, we also need to define how close our measurement is. And in order to introduce that, I need to discuss a few more properties of the boundary spectral data. Okay, so now let's take a sequence of eigenpairs, which consists of the eigenfunctions and the eigenvalues, and we can order our eigenvalues in an increasing way, and these eigenvalues will satisfy the Weil asymptotics, which means the kth one plus the absolute value of the kth eigenvalue, that is of order k to the power 2 over n. Okay, and by a combination of trace inequality, interpolation, and elliptic regularity, we can also show that indeed the h1/2 norm of the boundary for our Neumann trace of the eigenfunction is bounded above by a constant times our 1 plus our eigenvalue. Okay. These two facts, or these two bounds, we're going to need in the next slide. Okay. Now let's take M to be in the range between in the interval between n over 2 plus 1 and n plus 1. And let's also define a weight, omega k, by k to the power minus 2m over n. I'll explain the reason why we take m in such a way. And let's introduce now two weighted Banach space. One is for h1/2 of boundary. One is for complex numbers. So the way we define these two Banach space is that if we multiply the h1/2 norm of the function hk by omega k, or we multiply our absolute value of yk with our weight omega k, then the product or the sequence of the product will be both in this Banach space L1. Okay, now let me mention discuss why we choose M in such a way. So if we take the product of omega k, lambda k times omega k, then because of that Weil asymptotics, I should write the absolute value of it, will be less than or equal to k to the power 2 times 1 minus m over n. And because of our choice of m, we can show that this 2 times 1 over m, 1 minus m over n is less than -1. So that the sequence of this eigenvalues will be in this weighted Banach space. Because when we sum up k to the power 2 times 1 minus m over n, we'll have a convergence series. And this is also the same reason. For the same reasoning, we can say that the sequence of the Neumann trace of our eigenfunctions is also in the weighted Banach space. Okay, so all these discussions suggest that we shall define the distance of our spectral data to be the sum of, say, the Banach norm of the difference of psi1 minus psi2 plus the difference of the the eigenvalues, lambda 1 minus lambda 2. Okay? And also, we need some a priori bounds or assumptions for the coefficients. That's what we call the admissible set for coefficients. Now for the one form, let's take n greater than 0 and k greater than or equal to 1. And the admissible set for the magnetic potential will be that we have smooth potentials whose HK norm is bounded above by n. And for the electric potential or the scalar function, we assume that this is W1 infinity smooth, and its W1 infinity norm is bounded above by n. Okay. And now I'm ready to introduce our main result. What our assumptions were, suppose we have a simple manifold of dimension 2 or higher, and m is in a certain interval, and we assume that our A1 and A2 are smooth, in particular the HK norm where k is at least n over 2 plus 1. We need this to be large enough and depends on the dimension of our manifold. And our two sets of electric potentials are also satisfy certain a priori bounds, which I discussed in the previous slide. Also, we're going to assume that A1, A2, and Q1, Q2 agree on the boundary, so that when we in the proof we need to extend our coefficients. So making this assumption will ensure our extension has a certain regularity. Okay. Then what we could show is that the L2 norm, excuse me, of the difference of the solenoidal parts of A1 and A2, plus the difference of our electric potentials, they are bounded above by a constant which depend only on our dimension, our manifold and its dimension, our choice of this number m, and the a priori bound n. Okay. Times the distance of our spectral data. Okay, and this because of our powers or the exponents are in the interval 0, 1, so we can call this a Hölder stability. In other words, we can recover A1, A2, or the solenoidal part of our magnetic potential and the electric potential Hölder stably from our inverse spectral data. Okay. Before I go over the proof, let me mention a few known results, which are basically our motivation of studying this problem. The study of inverse spectral problem can be dated all the way back to 1929. Therefore, unfortunately, I cannot go over all the contributions in this study. If someone in the audience made contributions and I omitted your result, I sincerely apologize. Okay. So without the simplicity assumption, it was proved by Kochelev and Kurylev that the boundary spectral data does determine the solenoidal parts of A and the potential Q uniquely. That's a uniqueness result. And when it comes to stability, a few years ago, both Kurylev and Lasas proved that the boundary spectral data actually can determine the metric of our manifold G stably, but the spectral data is not the one for magnetic Schrödinger operator, but only for the Laplacian or the minus Laplacian. And the stability is honestly quite bad. It's double log stable. Okay. And with the simplicity assumption, including the Euclidean case, there were quite a few studies for this, all of which are sort of motivated our result. So in 2010, Ben Jude assumed that the magnetic potential is actually known, and they proved the stability for Q in the Euclidean space. And a year later, Belasud and Dos Santos Valera, they assumed that they don't consider the magnetic potential, and proved the L2 norm, the Hölder stability for the L2 norm of Q on simple manifolds. And that's from the spectral data. Okay. And in 2013, Julian and Stefanov also assumed that the magnetic potential equals to zero. And they proved the Hölder stability for the L2 norm of Q in the Euclidean space, given that the boundary spectral data are asymptotically close. So this is a slightly different type of assumption than 2011 result and ours. Okay. And a few years ago, a group of 5 authors extended the 2013 result to the setting of simple manifolds. So one major contribution about our result is that there were no earlier results which addresses the stability of the magnetic potential, or more specifically in this case, the solenoidal part of the magnetic potential. Okay. So now let me just briefly mention the main idea of the proof. This is actually a 2-part process, and due to time interest, I'll only discuss one part. So the first part in the proof, we show that the boundary spectral data, or the norm of the boundary spectral data, is bounded below by the norm of a hyperbolic DM map associated to a hyperbolic operator. Pretty much we add dt squared to our magnetic Schrödinger operator, which we started with the talk. Okay, yeah. Excuse me. This reduction step is actually, again, a 2-part process. We're not connecting the spectral data directly to a hyperbolic DM map. We're going to do this connection via an elliptic DM map. And that is the part of the proof I'm going to discuss in this talk. And how do we prove the hyperbolic stability result? That's more like a classical argument where we construct the geometric optic solutions to a hyperbolic problem, which reduces the stability of the unknown coefficients to the stable inversion of the geodesic ray transform. And this is the part we need simplicity. I'll mention briefly what we're doing, the hyperbolic stability, and why we need simplicity here. But what we believe is that for our step 1, the reduction step, doesn't require simplicity. It requires compact manifolds with boundary. So there is hope to extend our result to more general geometries. Okay. Yes. So before I discuss the reduction step, let me mention very briefly what we have in the hyperbolic stability. So let's recall that our A is a smooth one form with real valued coefficients whose HK norm is bounded above, and our function Q is also real value whose H1 norm is bounded above, and our hyperbolic operator is dt squared plus our magnetic Schrödinger. So we're going to consider this initial boundary value problem where we have 0 initial conditions and a non-zero Dirichlet condition on the lateral boundary of the spacetime. And at least for this part, I'll denote Q to be the product of our time interval. In our result, we need this time to be sufficiently large. And this Q is the product of the time interval 0t time and the manifold. And its lateral boundary is denoted by sigma. Okay. And what is the regularity of our Dirichlet value? That's in what we denote as L02. That's functions in L2 which is supported whose support is in this lateral boundary. Okay. And when we define the hyperbolic DM map, since our regularity is quite low, this DM map will map from L2 functions to H-1 functions. We're going to define our DM map in a weak sense. Okay. And when it comes to this hyperbolic DM map, there's also a natural gauge invariance. In other words, the hyperbolic DM map cannot determine our one form or vector field A uniquely. And the reason is pretty much the same as the gauge for the spectral data. So in other words, we could only hope to recover the solenoidal part AS and Q from the DMF. And that was our goal. Okay. And in fact, what we were able to prove is that the solenoidal part, the L2 norm of the solenoidal part and the L2 norm of the potential, they are both bounded above by a constant or by constant times the operator norm of the difference of our hyperbolic DMFs to a power between 0 and 1. So in other words, this is also a Hölder stability result for the hyperbolic operator. Okay. And there were also some earlier studies in the hyperbolic stability, or in general hyperbolic inverse problem. Again, I'll only mention a few results that are very, very closely to ours. Okay. In 2010, Benju, this is actually the same paper where Benju proved the stability for spectral data. They also proved the stability for H-1 norm of Q and the L infinity norm of dA in Rn from the hyperbolic DMF. And a year later, Bellasio and Dos Santos Varela proved the Hölder stability for the L2 norm of Q on simple manifolds. And in 2019, Bellasio and Rezik, they assumed that the one form doesn't exist, but took into a damping term into cooperation, a time-independent damping term, I should mention, and they proved the Hölder stability for the damping term and the scalar potential on simple manifolds. And 3 years ago, Arnaiz and Guillermo, they proved Hölder stability for Q, not on simple manifolds anymore, but some improvements on over simple manifolds. They proved stability on manifolds with strictly convex boundary and no conjugate points. These are also two properties shared with simple manifolds, but in their result, the manifold could have a certain trapped set of geodesics. This is something the simple manifolds cannot have. Okay. Yeah. And in the end, I want to mention that in all these results, the regularity for the DMF is that they map H1 functions to L2 functions. But in our problem, we have to shift the solid index one step lower to L2 to H-1. This is because of what we need to do in the spectral problem. In other words, the reduction step. Okay. Yeah. So a very brief sketch of the proof. We construct the geometric solutions to the aforementioned initial boundary value problem, and then we use these solutions to reduce the hyperbolic inverse problem to the stability of the geodesic retransform of one forms and functions. So this stability result, which is really an integral geometry question, is only known on certain classes of manifolds. This is not known in general. Okay, and this is the main reason behind our geometric assumption. And what is the geodesic retransform? So pretty much we're integrating either a one form or a function along a geodesic. Yeah. So here's how the geodesic retransform of one form is defined. And one thing I want to mention here is that the normal operator, which is I1 star I1. This I1 star means the L2 adjoint of I1. That's a bounded linear operator. Okay. And in this hyperbolic part of our problem, we are going to rely on this stability proved by Stefanov and Ullmann in 2004. And in this result, they proved their geometric settings on simple manifolds. And we have to be in line with the same geometric setting in order to apply our result. Okay. What they were able to show is that the normal operator for the geodesic retransform of both one form and functions, they're both bounded above by they're bounded above and below by a constant times the L2 norm of this either the solenoidal parts of our one form or the function itself. Okay. And the hyperbolic stability in 2022 by Arnaiz and Gillen, they relied on a similar result as the Stefanov and Luhmann in 2004, but on the same geometric setting as in their 2022 paper. Yes. So I think I have about 15, 20 minutes left. So let me now start talking about the last part of my talk, which is the reduction step. Okay. So we're going to connect this reduction step connects our spectral data and the hyperbolic DM map. We're going to do it with the help of an elliptic DM map. So let us now recall that our dA is d plus IA. D is the exterior derivative, A is a one form, and our magnetic Laplacian is dA star dA. And for any number in the resolvent of the magnetic Schrödinger operator, we're going to take f to be a h1 half function. So let's consider this boundary value problem where we have our magnetic Schrödinger operator, but shift this operator by this constant z, and the Dirichlet value is given as f. Okay. And we're going to define this elliptic DM map, which maps from h1 half functions to h minus 1 half functions in such a way. Okay. And again, this DM map is defined in a weak sense due to the low regularity of our function of our boundary values. Okay. And what we were able to show is that now this DM map is from h1 half to h minus 1 half. Indeed, if we take s to be any number between -1 and -1 half, we have a bounded operator for this DM map, which maps from h1 half to hs. Okay. Yes. And in our connection or reduction from spectral data to hyperbolic DM map, we're going to also need this resolvent operator. So now if C is in the resolvent, then consider the non-homogeneous boundary value problem, where we also have the magnetic Schrödinger operator shifted by Z, but we have an interior source, but homogeneous condition, Dirichlet condition on the boundary. Then we define this a resolvent operator, which is holomorphic Banach space valued with such a representation. We see that here in this representation, we got the eigenvalues and the eigenfunctions. Okay. So we're starting to make connections between the elliptic DM map and the spectral data. Okay. So ideally, we want a formal representation of this elliptic DM map in terms of the boundary spectral data, which consists of our lambda k and psi k. But one issue here is that now we are looking at an infinite series here. So we need to make sure the series is absolutely convergent, but it's not in some cases. So we cannot really write such an equation. That's the reason why I put a quotation mark here. So one way to work around this issue is that instead of DM map itself, we're considering higher order derivatives of the DM map. Then one could show that there's a formal representation of the mth order, where m is sufficiently large, the mth derivative of the elliptic DM map, that can be written as a certainly convergent power series, a certainly convergent infinite series, which also includes lambda k and psi k, the spectral data. And it was shown by two groups of authors that when M is sufficiently large, this series is absolutely convergent. So we can remove the quotation mark in the equality here. Okay. And now we have connected the elliptic DM map with the spectral data, and that was connected elliptic and hyperbolic DM maps. Okay. So earlier we defined our hyperbolic DM map to be functions from L, here I should write L0 to, from L0 to H minus 1. Then we consider its restriction to a higher order Sobolev space of such regularity, where we have H to the 2n plus 4. And for many time derivatives of our function, it vanishes at 0. Then in this lemma, we showed that this restriction of the hyperbolic DM map can be written in terms of those derivatives of the elliptic DM map evaluated at z equal to 0, apply it on some time derivatives of our function f, okay, with a certain remainder term. And this remainder term, the expression I will not write, not to bother the audience, but the catch here is that it's a bounded operator that can be expressed in terms of our spectral data, lambda k and psi k. Okay. So now if we want to bound this hyperbolic, the restriction of the hyperbolic DM map, it is equivalent to bound these first n plus 2 terms and the remainder term. And we're going to do that next. Okay. So what makes our problem more challenging is the following. In earlier works where they assumed either A is 0 or A is known, then one can show that if we're considering this elliptic DM map, which maps from H3 halves instead of 1 half to HS, where S is between 0 and 1 half, then the operator norm of the elliptic DM map is bounded above by this power of z. And they can also show that the derivatives of the DM maps, that is also bounded by certain powers of z. So now when we also include the magnetic potential in our problem, the second inequality remains the same, but the first inequality will change. The power of z will change from s over 2 minus 1/4 to s over 2 plus 1/4. So there's a shift of power by z. There's a shift of z to the power 1/2, but that pretty much makes our problem much more difficult. Okay, and that's also the reason why we're shifting we're changing the regularity of our elliptic DM map from H3 halves to HS to H1 half to H1 half mapping to HS, where S is between -1 and -1/2, because we want to make sure that this exponent is negative for a reason I'll discuss in a few moments. Okay. And what we were able to show in our paper is that suppose again now our delta means the distance of our spectral data. Then in the sum or in the representation for the hyperbolic DM map, we could bound the first n plus 1 terms by such inequality, some powers of z, and the norm of the spectral data. This is for j between 0 and n, and for the n plus 1 derivative, this operator norm from H1 half to HS is bounded by a constant times the norm of our spectral data. And the same bound also works for the remainder term. Okay, now let's put everything together and see why we have to have s between -1 and -1/2. So we are going to, so in order to estimate our hyperbolic DMF, or in this case, the restriction of the hyperbolic DMF, we are going to use the bounds we established in the previous slide. And for those, that will give us, in the end, such an inequality, or in particular, this function, which involves delta and absolute value of z. And from here, we want to obtain a minimum value for this function, and that requires this power s/2 plus 1/4 to be negative. Because n plus 1, obviously, that has to be positive. And if both powers are positive, then we cannot obtain a minimum value. Okay, and that minimum value is a certain power of delta. And this power is between 0 and 1. I think this power depends on s and n. Okay, it's written in a specific expression, which I omitted in the talk. Okay. Yeah. And so this inequality is true when delta is, say, small enough, and when delta is not very small, we can also show that this function in the parentheses is also bounded above by a constant times the spectral norm itself. Okay. I omitted quite a few details in the slides, and in particular the hyperbolic DMF part. For details, I'll be happy to discuss them after the talk, and also they're included in the paper which we posted on arXiv over the summer. Okay. Thank you very much.